from a tree, Newton has his aha moment. But what if that apple bounced, swung like a pendulum, or interacted with another apple midair? Welcome to the wild world of physical reasoning. Today we dive into the Denoising Hamiltonian network, a neural network that doesn't just predict one step at a time, but learns global physical rules. It's like giving Newton a futuristic assistant that can simulate, interpolate, and even guess hidden forces, all while staying faithful to the laws of physics. By blending Hamiltonian mechanics with a denoising twist, yep, like diffusion models, this framework handles noisy data, sparse observations, and chaotic systems like double pendulums with surprising elegance. Now buckle up. We're about to drop the apple into DHN's world.
Imagine trying to teach a neural network to respect the underlying laws of physics rather than just fitting data. That's the challenge the authors tackle right away. They point out that most approaches build physical rules directly into the model, often using ideas from classical mechanics. This works decently, but tends to focus on short-term predictions and forward simulations only, ignoring tasks like filling in missing data or estimating unknown parameters. To move beyond these limitations, the authors present the Denoising Hamiltonian network, or DHN, which I'll call DHN for short from now on. It blends Hamiltonian mechanics, the formalism that uses energy to describe a system's motion, with the adaptability of neural networks. DHN has three main strengths. First, it processes sequences of system states as tokens, so it sees bigger time chunks rather than just consecutive steps. Second, it borrows denoising ideas from diffusion models, meaning if the predicted trajectory becomes noisy, the model can pull it back onto a physically valid path. Third, it includes a shared global latent code that tells the network about each system's unique properties. This lets one model handle multiple different physical systems. They test DHN on three key tasks: predicting and completing trajectories, estimating hidden parameters from partial observations, and doing interpolation, like super-resolution, in time. This framework aims for a more flexible and capable way to integrate physics into neural networks. After wrapping up the introduction, the authors emphasize these same three innovations from another angle. They highlight sequences as tokens for chunk-based reasoning, a denoising process for keeping forecasts on track, and a global conditioning mechanism for handling multiple systems in a single network. They then move into related work. First, they talk about Hamiltonian neural networks, or HNNs. HNNs bake physical principles, especially conservation of energy, right into their architecture. While HNNs handle simple systems well, they don't always generalize to multiple systems or sparse observations. Next, they discuss operator-based methods like physics-informed neural networks and Fourier neural operators, which are powerful for partial differential equations, PDEs, but can be less suited to discrete dynamical systems. Then comes the start of the methods section. The authors pose a question. What sorts of physical relationships can we model besides the immediate next step? Look at figure 2 here. It illustrates three approaches: solving the entire trajectory at once, global equation, marching forward step by step, numerical integration, or directly relating distant states using conservation laws. That third idea is particularly intriguing and sets the stage for a model that can handle more abstract, long-range dynamics. The authors now turn to the core principles of how the model learns physics. They begin with Hamiltonian mechanics, which uses position, Q, and momentum, P, to describe a system's total energy. In this formulation, the Hamiltonian is a function that encodes a system's energy. The system's equations of motion follow from the gradients of this Hamiltonian. HNNs take this idea and make the Hamiltonian a learnable function, comparing the gradients of that function to observed motion as a training signal. The paper then discusses an improved approach, the discrete Hamiltonian, which jumps in time more directly. Instead of integrating step by step in a traditional manner, it uses gradients from a discrete Hamiltonian to move forward. This approach can reduce the integration errors typical of standard numerical methods. Check out figure 3 here. Try them. It shows boxes for each time step, with arrows connecting Q and P across time steps using these gradient-based updates. That's how the model tries to respect the structure of Hamiltonian physics, instead of just predicting blindly. The authors note this update rule can be implicit. You might need to solve an optimization problem to predict future states. That motivates the introduction of denoising, which will come into play to keep everything manageable when real data gets messy. Next, we see how the authors tackle noisy or incomplete data while still honoring the laws of physics. They extend the discrete Hamiltonian idea into a blockwise form. Rather than predict just one future step, the model looks at a small group or block of time steps, updating them all at once. If you look at figure 4 here, you can compare a standard HNN's single-step approach, on the left, to the block-based approach, on the right. Instead of stepping forward by one, it processes a block of 4 time steps, advancing 2 steps at a time, which captures longer range dependencies. Now for the denoising mechanism. Instead of simply zeroing out data, the model applies structured noise. Look at figure 5 here. It illustrates both binary masking, where entire states are dropped out, and soft noise, where the model slightly perturbs values. These corrupted inputs encourage the network to learn to reconstruct physically valid states, even under uncertainty. During training, the loss function compares the model's predictions for the future position and momentum to the ground truth, and penalizes the errors. Equations 11 and 12 in the paper show how a binary mask and random noise combine to form these corrupted inputs. Then, in inference mode, the model gradually denoises them. It works much like diffusion-based image denoising, but now for dynamical trajectories. Take a look at figure 6 to see 3 masking patterns they use. Autoregression, mask the end, super resolution, mask the middle, and random masking, mask arbitrary spots. This suite of masking strategies teaches the model how to handle a variety of real-world data problems. Now we zoom in on the architecture details. The model is a decoder-only transformer, reminiscent of GPT. For each time block, it takes in position and momentum values, along with information about which parts are noisy, then runs a self-attention process to figure out how states across the block relate to each other. One important twist is the global latent code, sometimes called a global conditioning vector. It's basically a learned token that tells the network about the overall identity of the system or trajectory. For example, different pendulums might vary in length or mass. This global code is treated as a query token, guiding the transformer when it predicts how the Hamiltonian evolves. The noise scales are also passed in, signaling which parts of the input are corrupted. To learn these global codes, the paper uses an autodecoder approach. Each trajectory gets its own learnable vector in a codebook, which updates during training. Later, at inference, the network weights are frozen, and only the code is tuned for new systems. This trick helps the model adapt quickly to new data. The authors then describe their experiments. They focus on single and double pendulums. The single pendulum is simpler, with well-defined energy conservation, while the double pendulum is known for its chaotic, sensitive to initial conditions behavior. The first task they tackle is forward simulation. During training, they hide the last few states in a block, autoregressive masking, and ask the model to fill them in, so it learns to march forward in time. How well does DHN handle forward simulation? They put it to the test on 1,000 trajectories from these pendulum systems. The model sees the first 8 time steps and must predict the next 120. Look at figure 9 here to compare DHN to several baselines like HNN and simpler neural networks. On the single pendulum, DHN shows lower error over extended timescales and conserves energy more faithfully. Traditional methods can accumulate tiny errors that blow up over many steps, but DHN's denoising helps keep it stable. For the double pendulum, things are naturally trickier since the system is chaotic. Still, DHN outperforms others, retaining smoother energy profiles and a lower average error across time. Then there's the question of how well it generalizes to new trajectories, ones not in the training set. By optimizing just the latent code for those novel trajectories, DHN still predicts them accurately. They also probe how meaningful these learned codes are. After training, they freeze the model and use a basic regression head to see if the latent code can reveal a hidden system parameter, like the length ratio of a double pendulum's arms. Sure enough, DHN's representations do a great job capturing these physical details, suggesting it really learns something about the underlying physics, not just patterns in the data. Next, we see results for trajectory completion. This is where the model has only partial observations of a trajectory and must fill in the rest. Check out figure 10 here. DHN, shown in pink, beats both HNN and simpler architectures such as ResNet and transformers. In the single pendulum case, DHN keeps the prediction error small and the energy drift in check. Even with the double pendulum's chaotic swings, it stays relatively consistent, while other methods blow up in error. They also revisit latent representations with a linear probing test, freezing the learned codes and training a simple regressor to predict the ratio of the 2 pendulum arm lengths. Look at figure 11. DHN gets the lowest error by a wide margin, reinforcing that its latent space encodes genuine physical structure. Finally, The authors analyze block size and stride, how many time steps to group together, and how much to shift these groups. Figure 12a shows that a stride around half the block size is optimal. Too little stride means too much overlap, which can lead to repetition or overfitting. Too large a stride might reduce temporal coherence. Figure 12b uses diagrams to illustrate how overlap can help or hurt. The main lesson is that it's not just about having a fancy model. The exact setup of blocks and strides can really affect performance. The authors then explore interpolation, asking the model to guess all the missing states when large chunks of the trajectory aren't observed. They do it using progressive super-resolution. At stage 0, the data is very sparse, and each subsequent stage, stage 1, then stage 2, and so on, fills in finer details. Check out figure 13 to see how this is set up. The global latent code is used at every stage, so the model stays consistent about which system it's dealing with. They test this in 2 scenarios. One where the initial conditions match the training distribution, and another where the model faces a distribution shift. Figure 14 compares DHN to a convolutional neural network (CNN) approach. DHN performs better in both cases and is especially strong when dealing with unseen initial states because its physics-informed framework generalizes beyond the exact situations it was trained on. Wrapping up, the paper reflects on what it means to embed physical reasoning in deep networks. The authors argue that going beyond one-step forecasting is crucial. We should look at parameter inference, trajectory reconstruction, and interpretability, essentially treating the entire system as a global reconstruction task. They even hint that data-driven models might learn physical laws in the same way large language models pick up grammar rules. The paper ends with a call to explore even more complex systems and architectures, carrying forward this idea of weaving physics into deep learning for more robust, versatile models. Thanks for joining us today. Happy exploring!